In this video, we discuss about the paper titled A Note on Maximal Acceleration. This paper has three main results. One of them is the maximum acceleration of a quantum particle is directly related to the speed of transportation in the projective Hilbert space. The second one, the minimum space uncertainty answer is inversely proportional to the maximal acceleration of the particle. So it is third one, it is argued that the most accurate clocks are those which can be maximally accelerated. Let's see how these results are proved. First, let's start with considering a quantum system. Let S be the quantum system characterized by normalized vector psi. If A and B are the any two physical observables, then they satisfy the Heisenberg uncertainty relation. So let's choose B to be the Hamiltonian of the system. Then this expression reduces to this form, and consider A to be an observable of the system that does not depend on time explicitly. So then we can write this expression as this form using this is the standard expression for the time evolution of the physical observable. So by taking A to be the velocity of the operator of the particle, so defined through this equation, V is defined like this, then the right hand side we get is this form A to be V. So this quantity on the right hand side of the equation 4 is nothing but the acceleration of the particle if we make use of Nernst's theorem. So this inequality we can write in terms of acceleration. So we get an upper limit for the acceleration which is given in equation 5. So from special theory of relativity, we can one can say that the limiting speed of any particle is the maximum the maximum attainable velocity is c, right? The velocity of any particle could be c. In the maximum it could be c. So the delta v, if we consider it as c, the maximum value c, then we arrive at the maximal acceleration limit which is given in equation 6 by substituting delta v as c. So we want to give a geometrical meaning to this inequality. So for that, let's consider a state which satisfies the Schrodinger wave equation and take the another state at the time t plus dt. The distance between these two states is given by this expression. This is the taking the inner product. This is expressing this quantity, we can get the norm distance function. This is the norm distance function given in equation 7. So by using Taylor's expansion, this psi of t plus delta dt can be expanded up to second order. Then we can get an expression for the inner product of psi of t and psi of t plus delta t plus dt, and you get the equation 8. Now by substituting that, the normed distance function can be written in terms of fluctuation of energy. So from this quantity we will define a new quantity known as the speed of transportation, which is given by the fluctuation of energy and the Planck divided by Planck's constant. So this is the speed of transportation. But in the expression of the acceleration, what we have got from the inequality here, we have an quantity delta h in it. Right now we substitute speed of transportation in the place of fluctuation in energy, and we get a maximal acceleration is expressed as 2c vh. Vh is the speed of transportation in the projective Hilbert space. So from this expression we can get to the theorem that if the wave function of the whole system is an eigenfunction of the total Hamiltonian, then the system cannot be accelerated, because the delta h, the fluctuation will be 0. So A max becomes 0 from this expression. So that's why if the wave function becomes is an eigenfunction of the Hamiltonian, then the system cannot be accelerated. Now consider the we will define the uncertainty in the space time. Yes, it is defined like this: derivative with respect to x and delta x. Delta x is the uncertainty in the spatial coordinate of the particles. So using the Heisenberg uncertainty relation, in the place of A, if we take the position of the particle, then the right hand side will be the velocity of the particle, right? So this is the velocity of the particle, and we can express the uncertainty in the space time by substituting in the place of delta x. We can get the lower limit for the minimum uncertainty as given here in the equation 12a. So in place of delta h, we can write speed of transportation as we defined earlier. So the lower limit for the uncertainty is defined in terms of speed of transportation. So from this expression we can find that the minimum uncertainty in space time is inversely proportional to the speed of transportation in the projective Hilbert space. So what is the maximum value for VH? VH is given by C by A max, right? So if the test particle accelerates to much higher value, then the minimum uncertainty can be reduced to a greater extent. So what does it mean? It means that inaccuracy, if R is the inaccuracy with the clock, and it is clear that most accurate clocks are those which can be accelerated to a greater extent. So this is the result what they got in this paper. Thank you.